Hello and welcome. Today, we are taking a journey right into the heart of reality itself to break down one of the most successful theories in all of science, the standard model of particle physics. So let's just jump right in with the biggest question of them all.
It's the ultimate question, isn't it? What are you, me, the stars, and everything in between really made of? For centuries, this one question has driven our brightest minds, pushing us to look deeper and deeper into the very fabric of the cosmos.
You know, the world we see around us is really just the surface. The real action, the fundamental rules that govern everything, it all happens in a sub-microscopic realm. It's a place so small and so strange that it operates by a completely different set of laws. And that's exactly where we're headed.
To get our heads around this world, we first have to understand scale. So, we're going to take a trip from the impossibly huge all the way down to the building blocks of reality itself.
Let's start at the very top. This number, right here, represents the entire observable universe in meters. It is a scale that is almost impossible to comprehend. But we're going in the other direction.
And now, after a leap of 37 orders of magnitude, we land here, the scale of a single atom. This is the basic unit of all the matter we're familiar with. It's a jump from the cosmic to the microscopic that is truly, truly mind-bending.
Yep, that's right. Everything you can touch and see, from your own body to the earth beneath your feet and the sun in the sky, is built from these tiny, fundamental structures. Atoms are the Lego bricks of our entire macroscopic world.
But here's a deep, mind-boggling truth. An atom, the very thing we just called a building block, is almost entirely nothing. That staggering percentage right there is just empty space. The solidness that we feel is really just the effect of invisible fields and forces holding tiny little particles together.
So if atoms are mostly empty space, what are the actual bits of stuff inside them? To answer that, we have to go down one more level and meet the first of our two fundamental families of particles, the fermions. Physics neatly divides all fundamental particles into these two groups. You can think of it like this. Fermions are the bricks, the actual substance. Bosons are the mortar, the forces that hold the bricks together. Fermions have this 1 per seat rule, which is literally why matter is stable and you don't fall through the floor. Bosons, on the other hand, can pile on top of each other.
Let's focus on those bricks, the fermions. They themselves are grouped into two types, quarks and leptons, and they come in different generations, almost like different weights of building material. And this brilliantly lays out the particle zoo of matter. Now, don't feel overwhelmed. The absolute crucial takeaway here is that all the stable matter we see every day, protons, neutrons, electrons, is made entirely from that first generation. The up and down quarks combine to make protons and neutrons, and the electron orbits the nucleus. The other two generations, they're much heavier, unstable copies that only show up in high-energy events, like in particle accelerators.
Okay, so we've got our matter bricks, the fermions. But how do they talk to each other? How do they stick together to form atoms, molecules, and eventually us? For that, we need the mortar. We need the bosons.
The Standard Model describes 3 of the 4 fundamental forces of nature. The electromagnetic force, carried by photons, is responsible for light and chemistry. The strong force, carried by gluons, is incredibly powerful but acts over tiny distances, basically gluing quarks together inside protons and neutrons. The weak force, with its W and Z bosons, governs how atoms can change from one type to another, like in radioactivity. And notice what's missing? Gravity. It's the one force the Standard Model doesn't explain.
We have matter and we have forces. But there's a huge question we haven't answered yet. Where does mass come from? Why do some particles have it and others don't? To solve this, we need to introduce the last and maybe the most famous particle in our model.
You know, this was a huge hole in the theory for decades. The equations worked beautifully, but only if all the fundamental particles had no mass, which we knew just wasn't true. The electron has mass, quarks have mass. Something had to be giving them that property.
The solution was a brilliant, weird idea. Imagine that the entire universe is filled with an invisible energy field, kind of like a thick cosmic syrup. As particles move through this field, some of them feel a drag, a resistance. That resistance is mass. Particles that interact strongly with the field, like the top quark, are really heavy. Particles that barely feel it, like neutrinos, are super light. And particles like the photon that don't interact at all have no mass.
And the Higgs boson?
That's just an excitation, a little ripple in this cosmic field. Its discovery was so crucial to confirming this whole picture that it earned this famous, if a little controversial, nickname. It's the physical proof that this mass-giving field is real.
And they found it. In 2012, scientists at the Large Hadron Collider at CERN announced they had detected the Higgs boson. It was the final missing piece of the Standard Model puzzle, a triumph of theoretical prediction and experimental genius that was decades in the making.
So the Standard Model is complete, and it is incredibly successful. But it also reveals one of the most profound mysteries in all of existence, a mystery tied to a ghostly twin of matter.
The theory predicts that for every particle, like an electron with its negative charge, there should be an equal and opposite antiparticle, an anti-electron or positron with a positive charge. Same mass, opposite charge. A perfect symmetrical mirror.
But here's the catch. When a particle meets its antiparticle, they don't just bounce off each other. They annihilate completely, converting their entire mass into pure energy with 100% efficiency. Poof, they're gone.
So the huge question is, if the Big Bang created equal amounts of both, why is anything left? Why didn't it all just cancel out? Well, the theory suggests the balance wasn't quite perfect. For every 10 billion particles of antimatter, the universe created 10 billion and 1 particles of matter, a tiny, almost unnoticeable imbalance.
After all the annihilation was over, that 1 in 10 billion leftover became everything. Every star, every galaxy, every planet, and every single atom in your body is a survivor of that initial cosmic war. We are the leftovers of a near-perfect cancellation.
And that leads us to our final profound question. Why? Why this preference? Why did the laws of physics favor matter even by such a tiny amount? The Standard Model allows for this kind of asymmetry, but it doesn't fully explain it. Unlocking the secret isn't just a matter of curiosity. It's about understanding the ultimate reason for our own existence.